Hello, everyone. My name is Avihu. I work at StarkWare. I'm StarkWare CPO. Guys on the side, if you can just, excuse me. Hello. Great. So I see a lot of faces I recognize, and that's great. I'm going to present in just like something like 15 minutes. Let's see, starting from now. This idea of ColliderVM, which is basically how one would do verifiable stateful computation on Bitcoin without the need to use fraud proofs. Okay, so let's go. What am I going to present in those 10, 15 minutes? Basically, I'm going to start with explain what do I mean by stateful computation. Then really, really quick, I'm going to go over the solutions that exist today. And then next, I'm going to talk about ColliderVM. What is it? What's the motivation? How does it work? And then finally, if I will have time, I will touch a little bit about what's next. Okay. So what do I mean by stateful computation on Bitcoin? I mean, I want to run a computation on Bitcoin or to verify a computation on Bitcoin that has the ability to persist on-chain across multiple transaction user interaction. What exactly does it mean? So the most rich example of this that you can think of is of a smart contract, right? And this is something that has code. You always know what code you interact with. And this code also has some state, so it can know what happened in the past, and it can use this state to do things in the future. But smart contract is a very rich form of stateful computation. And for the needs of many, many protocols and computation on Bitcoin, it's enough to actually degregate it to something, first separate it and then degregate it a bit. So I'm going to separate it to two things. One is logic persistency, and the second one is data persistency. What do I mean by each? So, sorry, just a second. Logic persistency is the following. I mean that at each point in time that someone interacts with the code or the program, they know at which state of the program they are going to interact with. Every time they call it, they run a function, they know deterministically which function is going to be called next, which function they're calling now. And data persistency means that in between different calls of different functions, there is information that can be passed and used. So at the very least, smart contract is like a rich form of that because you can manipulate the data many, many times. But at the very, very least, I want the ability to read the same data between different functions. Okay, motivation. Why would you want something like that on Bitcoin? So here are two examples on why would we want to do something like verifying stateful computation. One is, well, sometimes you have a computation that is longer than 4 megabytes or has other limiting factors so that you can't really include it in one transaction, even in one non-standard transaction. And then you want to split it to a couple of transactions, right? But how do you do it on Bitcoin today? That's not something that is straightforward. And the second motivation is that sometimes you start a computation. For example, you lock Bitcoin, but you don't know what necessarily will be the end of this computation. For example, you don't know who will receive this Bitcoin under what conditions. So what you want to achieve in this case is that there will be different point in times that will interact, that where users will interact necessarily with the same logic. Okay. What solutions exist today? So the first and most obvious solution, or maybe I should call it a non-solution, is multisig. Well, basically in multisig, you have usually T out of n assumptions. You pick a threshold T, and you have n signers, and the n signers, at least T of them should compute whatever you want. So they can run any computation in the world, and they just sign that T of them actually verified it, and they sign it for you. The obvious problem is that if you use a small t, then you don't have to have many of them live, but there is a risk that they will be dishonest. And if you use a large T, let's say T equal N, then the problem is that if one of them isn't functioning, then you can't complete your computation. And that's annoying. So for us, it will be a non-solution. All right. Then going to the other extreme, we can also think of the notion of strong covenants, and that requires some sort of soft fork. And if you have that, you can get the strongest form of logic and data persistency, which means that you can actually mimic smart contracts fully, at least with CAT, and possibly also with things like CTV. Right. And then the last solution and the best solution in the market is BitVM. And the nice thing about BitVM is that, well, it has many, many variations, but in all of them, the trust assumption is 1 out of n for security and for liveness most of the time. Okay. So BitVM has the following the following ways to solve those issues. On logic persistency, what you do is you take your transactions and you pre-sign them in some order. That ensures you that only the flow that you pre-signed will be, one of them will be executed. You don't it doesn't have to be one flow, but there is a set of flows that you pre-sign, and all of them can be executed one after the other. And the way that you solve data persistency, that you make sure that all the data move between transactions, is, for example, by using Lamport signatures and doing fraud proofs on them. That's one way to do that. Now the question is, can we get to the same goal using still pre-signed transactions for the logic persistency, but without relying on fraud proofs and doing the computation directly on chain? So like you can guess, this is what we do with ColliderVM. And the way to achieve data persistency with ColliderVM will be basically to use collision-based commitments. We'll show it in a second why it's needed and what is it exactly. And then you can do the computation actually directly on chain. So there is no fraud. You don't have to wait for someone to observe the computation and then detect fraud if it's there, but you can actually run the computation directly on chain. Okay, this was all very abstract. I'm going to give a slightly less abstracted example just for you to understand the problem, and then the solution. And then if I have time, I might have time, I will try to get into what's next. Right. So let's take a very slightly less abstract, but still an example that is abstracted. Let's say we have three functions, f1, f2, f3. And what we actually want to achieve is that we want to compute f1, and then we want to compute f2, and then we want to compute f3. We want to check that all of them return true on the same input x, right? So the easy thing is that, well, as long as you live with that, you will have a group of signers that will pre-sign this template. So they will say you can only spend f1 to f2 and f2 to f3, and only if you satisfy them. That's great. But now comes the issue, right? You can provide X to every transaction, but remember that when you do pre-sign those transactions, you don't know what X is going to be, what's the input for the transaction actually going to be. And because of that, there is a small issue. The small issue is that whoever calls those transactions can provide F1 with some X, but then provide F2 with a different X. And the script or the transactions will not be aware that they are executing on different X. So that's an issue. So we have logic persistency, but we don't really have data persistency. How? So let me just walk you through really, really quick on the trick or how you actually solve it. So let's just try solutions. That's the best, the most detective way to do it. So let's just assume that, okay, let's say we want to provide X that is some number of bits. So one way to do it would be to say, okay, let's say I want to provide X that is D bits, right? Then I can prepare many copies of those pre-signed transactions, and then make sure that in every transaction, we check that X is equal to some value of D, right? But the problem with, so this works, but the problem is that you are very limited with X. Like, you can transfer X equal 1, 2, 3, up to some number. But if you want to actually communicate D bits between transactions, you will need 2 to the power of D different setups, which is quite a lot. And most of the time when you run a computation, you need to communicate way more than D bits to many functions. So that's not a good solution in the general case. But what you usually do when you have a lot of information that you need to communicate is use hash functions, right? And this is the solution that is basically presented in ColliderVM. So the idea is this: if you have X can be now arbitrarily large. In order to communicate it to all those transactions, you will need first to do some work. What is this work? You will need to find the nonce where the hash, some hash that I will touch it in a second, of the X, the input that you want to communicate to all functions, and the nonce, the hash of it is equal D. And now, like before, you have several copies of this structure, but now the number of copies can be way smaller. Let's say 2 to the power of 20 or 30 copies, so 1 mega to 1 giga copies. And then you can use weekend hash functions that will enable you to find collisions. And the property that we are using here is the following: to find for a particular input nonce that fit to a collision with 1D is much easier than to find 2 different inputs that match the same D. It's just a much harder problem. So I'm not going to get into the math, but this trick enables us, if we have a large enough set of pre-signed transactions, it enables us to communicate X with a reasonably good level of security without doing extreme amount of work. All right, that's the basic idea. And now I want to talk about what are the good things here, and obviously then what are the bad things. So the good thing is that you can execute the computation immediately on chain. Like, you can call the transaction, and well, depending on the number of transactions and the number of blocks that you need, but let's say if you have 3 transactions, you can include them one after the other, and you don't have to wait. The moment they are done, your computation is ready. The flow is quite simple because you don't have to wait for outlookers, or you don't have to trust them, or you don't have to wait for their fraud detection. And then there are small things that I won't get into, even that I see that most of the audience actually knows BitVM pretty well. So, but I will skip that just because of time. And one cool feature that maybe you can also achieve in BitVM, but it's clear to me that you can achieve it here, is that you can also open the set of operators to be, for instance, any miner or anyone who can interact with miner and push transactions. That's a cool optional feature. What are the drawbacks? So, all right, it really depends on what exactly is the computation that you are trying to do. But I'll say that without any soft forks, this setup phase is pretty expensive because you need to create a lot of copies for the signers to sign. And then you have to ask the operators to store them. So if it's 1 megabyte or 1 gigabyte, that's fine. But if it's 1 terabyte, that's already a problem. The second thing is that the off-chain cost of actually getting the collision is non-trivial. You can use things like off-shelf ASICs that already exist in mining, and you can do something like 2 to the power of 60, and that probably is fine. I'll touch it in a second, but it's anyway non-negligible issue. And then obviously it really depends on the computation that you're running on-chain. If this computation is like not too heavy, then it's not going to be too expensive. But if you're going to do something like, let's say, a Stark verifier, then at this point in time, that's still very costly, right? So it's pretty expensive to run. Okay. So what's next on the front of ColliderVM? Well, first of all, we have a POC or demo in progress. I think one of the guys here I recognize is also working on it from the group. It is right now just a toy example, so it doesn't use like a strong security. But the cool thing is that we are using their off-the-shelf mining ASIC just to make it like more fast and still low cost, comparable low cost. And then the other thing is that if you want to use it for verifying proofs, so there is still a lot of work to be done. But the nice thing is that Stark verifier is pretty friendly to the properties of ColliderVM because of reasons I won't get into now. But basically, Stark verifier is flexible. So for example, if you double the number of queries in Stark, you can actually achieve better security because you have better sampling properties of X. So that means that even if you have a collision, one collision will not be enough, for instance. But it does require, to make it even close to be practical, you need some Bitcoin-friendly hash function. And it's not trivial that one exists, but this is something that is in ongoing research. Yeah, I do want to mention that with CTV, so I did see, I think Robin published something about BitVM with CTV, and I think with somewhat similar ideas and some new ones, you can improve ColliderVM with CTV to the point where, first of all, you can get rid of the signers, which is a good thing, and also I think you can get rid of the storage requirement. That means that the setup will be way lighter. That's it. If you are interested to learn more about it or to check the POC or to donate to the POC, then you're welcome to contact me, and I will connect you to the Telegram group and you can check what's going on there. Everything is also open source, so you can also run it yourself. Thank you very much.